Uh, this will be we will talk about the Runge Kutta first order numerical method to approximate a differential equation. So basically, you need to the idea is if we have the differential equation usually will look like x dot equal to certain equation here, and this x can be a matrix. Okay, so maybe we have x1 dot s2 dot s3 dot, and each one you will have certain common equation related to the x1 function, x2 function, s3 function. So for example, this one usually it may look like this one, s1 dot. Actually, x1, s2, s3 they will have certain differential equation. S2 will be the differential of x1. S3 will be a differential of x2. So equation may usually will look like this one, 0, 1, 0, 0, 0, 1. If x1, x2 they are independent they are not coupled variables. So and this one you may have certain value 2, 3, and 1, something like this one. So each equation we can, for example, for this one we will get s1 equal to x1, s2, and x3 dot equal to 2x1 plus 3x2 plus x3. So if we want to know the parameter for the x3, for example, it is x3. And x3, the actual solution may look like this one. Okay, so if my initial point here, I have the initial value might be 1. And what will be if this is the delta t, what will be, how can we approximate this value? We already know this one, x3 0 equal to 1. For example, maybe this one is x3 1 equal to 2.5. How do we approximate this value? Basically, we can use the equation will be this method will be the simple one we call Euler method. So we can use x3 1 actually equal to f3 0 plus delta t multiply the slope x3 dot 0. We can use this slope multiply st to get the x3 but if the equation, if our curve is the linear curve like this one, 1 1, then this is 2.5. The problem is if our curve is linear function, is a line. When we use this method, Euler method, we can get a very good approximation. But if it is a curve, because the slope here is identical to the linear, the slope of the line in this point, so if we want to get if our line is not a slope, it's like this one, and our slope in the x3 0 is maybe a very small slope, so the approximation will be here. You will get the approximation will be here. You will have a large error. Okay, but if you try to, the delta time is not so large. You can see if we enlarge only this part, it may look like more like linear function. So the slope here can actually approximate the result better. For example, this might be 0.01 second, not 1 second. So the approximation will be better. So you can try to reduce the delta time to get a better solution. Or the other method is, the other idea is, we actually can use more information to estimate the data. Actually, we want to, if this is 1 second, we want to get this slope, this average slope. How do we get this average slope? The Runge Kutta method, basically we use 4 points. We can find one solution here. We can get one slope. And in this middle point, we get 2 slope. In the end point, we also get the other slope. And then you can find the slope. Some slope is larger than this average slope. Some is smaller than this average slope. Then we can try to do the average for all of the slope in different points. When we try to get the average slope by the 4 points, S1, S2, S3, S4 over 4. Basically, we can get a better estimation for this average slope. So this is the main idea for the Runge Kutta. We get more points to estimate what will be the slope between the average slope between the initial point, this point to the end to the next sample time point. So we want to estimate this average slope, and we use more points, not only the initial, the previous point. We can say the previous point here. For the Euler method, we only use the previous point to estimate. Assume here is the current point. We use the previous point slope to estimate the current. Where is our current point? Y value. Okay, or the x3 value. So we will talk about how do we implement this kind of method in detail. So assume we have the h. H will be our delta time. It means the time interval. Okay, so each time I want to estimate this point value. Use the previous point y0. For in the beginning, I have y0, and I want to estimate y. This will be the t0 plus h. I want to estimate this value. So basically, I need to estimate this is averages. What is this average slope? Okay, so basically we use this point to estimate what is the value for the y t0 plus 2h. We use the slope here to estimate this value, and when we have this value, we can get the slope here. Okay, and use the same equation. So then we also use this slope to estimate this value, but it will be also from the y0 difference. The slope is difference. So if I use this slope to average this value to estimate this the yt0 plus h over 2, you will get this point. Then I will get the other slope here. So I will use this slope to estimate yt0 plus h. So we will get certain point here, and we will get the other slope. So we try to average this one, this one, this one, and this one. Get the average slope. Then we can use the average slope to estimate what is this point. So the average slope, we also use the previous point and use this slope to estimate what is the point here. It will be, because we average four slopes, so the approximation for the average slope will be better. So you can see here, I use several. You can see, so the initial point here, we may have a slope. Then we use this slope to estimate what is the y0 plus 2h. So we get the, this f2 is the yt0 plus 2h. So we use the yt0. This part is t0 plus, because the time here is h over 2, delta time over 2. So it will be a h over 2 multiply the slope. I get as y equal to 0. We call it is f1. So I write here. So this is the f1. We use the slope multiply the time duration. We get at the previous point. So we get, it will be this point value. And if I say the h multiply the time, delta time multiply the f1 dot is k1, so this can become yt0 plus k1 over 2. Okay, so we get the second point. Then we can use the second point to estimate what will be our slope in this point, because we already have the equation. You do remember we have the f dot equation. F dot equation will be, for example, it will be for this example, it will be y dot equal to f dot equal to certain thing, certain governing equation here. Do you remember we have certain kind of governing, like x dot equal to certain thing in the I just replace s become y, no matter, you can understand. So because we have the differential equation for the first order, so we can get what is the slope in this point. If I have the input is the time and also the value, also the y value, so we can estimate what will be the slope in this point. So when we get the slope in that point, it might be look like this blue line. It might be look this line, okay? And then we will use this slope and also the initial, the previous point value y0 to estimate what would be if I time incremental the half of the time h over 2. What is the point if I use this slope to estimate? Not I use this slope, not this slope. Okay. So if I use this blue line to estimate the point, it will be yt0 plus h over 2 multiply the slope f2 dot. If h multiply f2 dot is k2, the equation reduced to this form. Then in this point, I can also get a slope. If I have f3 here, I have the y3. The f3 actually here, it is actually will be y t plus 2 t0 plus 2h y is equal to f3, and they will equal to this one, so it will get the point here. Then after we get this point, we have the other y t0 plus 2h. This value I use F3 because this is different from to this one. Because I use different slope to estimate. You need to be careful, do not confused about that in that. So if I have the value here, I can use this point value to estimate the slope. So I will get the third slope here. Then after I get the third slope, I can use this third slope to estimate what will be the point in after the time h, t0 plus h. So I use the slope yt0 plus h multiply, because the time become h, it will be a delta t, the time multiply the slope I estimate in the third point. Okay, so I will get this point f4, it will be the yt0 plus h. So in this point I will get the other slope. Therefore I get the fourth slope. It will be f1 dot, the first point slope, f2 dot, second point slope, f3 dot, third point slope, f4 dot, fourth point slope here. So after I got this fourth slope, I use the weighted sum. You can see I say the average slope should be this part is the average slope. You can see it is weighted. I use weighted for the first slope is 1, for the second slope is 2, for the third slope is 2, the last slope is 1. So it tells us we more believe the middle point slope, but we also want to use the initial point and the previous point and the next point slope to let the average slope better. Okay, so you can see it will be 1, 2, 2, 1. So all of the summation is 6. So we will over 6 to get the average slope here. So when we get the average slope, we directly use this average slope. This one is actually the average slope, f dot average. It should be this one. It should be after the average. It should look very similar to the actual average slope in this time. Okay. So assume it is very similar to the slope, so we will use the same rule, y0 plus the average slope multiply time, then we can get y1. y1 is here. It means the next point. Okay, this one is actually the yt0 plus h equal to yt0 plus the average slope multiply the delta t, and the delta it will be it is this one, because I just replace delta t become h, and the slope here will become f average will be this one, and the y0 is yt0, y1 here I mean next point, so it will be the yt0 plus h. Okay, so in each iteration, when you have the next point, you want to estimate the next point, it will be the t0 plus 2h. You will let this point become the previous point, and the t0 plus 2h become the next point. I already know this point, and I use this point to estimate next point value. So in this time, we will do the same procedure again to get what is this point. So it is an iteration. We need to do a lot of iteration until all the simulation time. For example, if we want to simulate from 0 to 100 delta 100h, so you need to do that 100 times. Okay, when on 100 iterations, so you can understand we need to use a for loop to help us do this iteration. And so you can see here, if this equation is like this one, then we already know h multiply this one is k1, and the f2 dot multiply h is k2. So this equation here should become 1 over 2, and k1 plus 2k2 plus 2k3 plus k4. Okay, this whole one will become this one, because we will write in the code, we will write something like this one. Be careful this part. So this will be the actual code. I give you a demonstration, and please, but you need to modify by yourself, because our Gamma equation is not like this one. So for example, if we have a Gamma equation like this one, and I assume my initial value is the 0.5. This Gamma equation is similar to our homework too, but it is not exactly the same one, so you need to multiply by yourself. Okay, so for example, our Gamma equation is mv dot equal to negative vb plus f, and our solution should look like this one. This should be our solution. So we already know the solution. You can try to derive the solution by yourself, but I will tell you the solution will be this one. This is the actual solution, and we only have these two functions, the Gamma equation and also the initial value. How do we use the Runge Kutta to approximate this analytical solution? It is our end to do. We want to get the problem will look like this one. So I assume the m is 1, b is 2, f is 3, and the start time is 0, v 0, and the end time is the 10 seconds, and my step size is 0.001. In your simulation, you can try to change the step size become 0.01 or become 0.1 or become 1. You can see if you let the step size larger, like 1 second or 0.1, the approximation will not good. But because the Runge Kutta use 4 points, but so even the step size is very large, like 0.1, you can still approximate the mass very well. But if you also implement the Euler master, if the step time is 0.1, the result may be very terrible. So you can see what is the inference. If you set different time step, you can try to modify this time step to see what happens. Then, so I will generate a time array. It will be from 0 to 10 seconds, and the interval is the 0.001. So then we will try to generate what will be our first point, because v number 1, it means the initial value. It will be equal to time equal to 0. So 1 initial value is 0.5 here. I put 1 because the index in the MATLAB, initial of the index in the MATLAB is 1. Okay, it's not 0. You need to be careful. And the T1 time equal to 0. Exactly solution. The initial value is also 0.5. The analytical solution. I call V exactly an exact analytical solution. So then what would be the, so we will write this part, we write a rock, actually we write a Runge Kutta here. So you can see I try to iterate from to time, the second times the, I from 2 to end of the time array. Why do we from 2? Because the first one, the first index is the initial value. We already have the solution, so we use the first point to estimate the second point until to the end of all of the point. So you can see I try to write a function. I have a function. This function we call f new f num. This actually is the is f dot. Maybe I should use df num. It will be more consistent with previous function, because I use f num. I say I define it is a function, numerical function. I did not say it is a differential function. Okay, I did not say it is slope. So how do I say that? I want to say this function actually it is a slope. You need to define a function called f numerical. It will help us to calculate the function. The function will be this function. So the f num it actually it is the v dot. Okay, it will be the negative v plus fm. It will be this function, so we can calculate the slope of the velocity. Fnum is this function, remember. So in the next slide, I will write a function called f numerical to help us calculate the slope of the velocity, and it will be implemented this function. It will be in the next slide. So in this, soon we already have the slope function here. So when I put what is the time, and so I will use the previous time and also the previous point. If it is 2 minus 1, so it will be v numerical 1. It will be this value. So I use the previous point as time equal to it will be in this time it will be t2. So I will use t, for example, if it is I equal to 2, I will use t1 and the v numerical 1 to estimate what would be our what is the slope during this time. The v dot 1. Be careful, this is the index. This is index. Okay, this is also index. It is not actual time. So actual time for t1 is 0 time. I use time, and this is also 0. This is also 0. And for t2 time here, it actually the interval is 0.001. So the time actually will be the 0.001. So you need to be careful. Inside it is index for the array. It is not the actual time. Okay, so 2 the actual time is 0.01. The second point, it means it is second point. This will be the first point slope, first point velocity, first point time. So you need to be careful, not confused about that. So in the second point, my previous slope will be this function, and this function multiply the time. I can get the incremental in the velocity. what will be I have the first point. This we call a V first point, and in the second point, okay, and as soon I have a slope here, this slope is the F. This slope is this one, and when I multiply the H, this is H. H multiply the slope, we can get this one. This one will be we call K1. It will be the incremental in the velocity if the time interval is H. Okay, so we get the first one K1, and then we can get second one. Second one here will be we try to find the middle point. Remember the second, we use the first one to find this one. It will be in the half time. So it will be the previous point plus the half time interval, and I also get the slope. This no, not the slope. I get this point value. This point value will be, I use the previous point. I want to the input should be the time. The time here will be the previous point. It will be a T1 for if I equal to 2, it will be T1 plus half H. Okay, this part is T1, and this part, so it will be a T, because I equal to 2, so it will be T1 plus half time interval. And we need to fit this point. What is this point? This point is I need to use the T1. I need to use the V1 plus the slope I calculate here, multiply it will be the FNUM multiply half H. So you can see FNUM multiply half H. It will be here. So it will be but we need to divide 2. So it will become plus K1 over 2. Okay, so we got this point. So we fit this point and also the time. We can get what is the slope in this point. So it will be the K2, the second slope, multiply the second slope. This part is the second slope for 0.2, and multiply the H. So it will be the incremental. If I have a slope here, and I have a time duration H, what is so this part is K2 incremental in the velocity. It is the K2 here. Okay. So when you apply the same rule, we can get the K3. K3 is we already have the slope here. We use this slope to estimate the half of the interval, the time interval. What is this point? And we fit this point, and also the time. Time is the half interval. We fit this point, and also the time here. This point will be, I use the previous point and the slope for the second point. This is P1, P2. So second point slope will be, we already get here K2. Slope multiply the time interval. But because our time interval is only half H over 2, so this one will be the K2 over 2. I use this slope plus H and divide 2, so it will be K over 2. I get this point and I fill this point here, so I can get this point slope. the third point slope P3. So after I get P3, I also start from the previous point. Use this to estimate what will be this part h after the time interval. The time interval is h. I get what is this point. So this point will be I use previous point. This is previous point. V numerical. I minus 1 previous point plus the slope multiply the K3 is the slope in the 3 of the point 3. The slope of point 3 multiply the time duration. So it will be the h. This part will be the slope multiplied duration. So it will be already. This is the K3. So I will add K3. I will get this one. So I fit here the point, the velocity value here, and also the time. The time is t, the previous point plus h. Then I can get the slope in the P4. This point is P4. So I get 4-point slope by this 4 equation. Then so I can say my next point, my current point, should be previous point plus the average of the incremental in the velocity in from 4 points. Okay, so it will be the K1 plus 2K2 plus 2K3 plus K4 over 6. This part is how do we increment after the time duration h, and we get 4. Remember we have for example h is we have 1 point, 2 point, 3 point, and 4 point. In the 4 point, we will get different duration. Maybe this is K1. We will get different incremental in the velocity. K1, K2, K3, and the K4. Then we average to get the average incremental in the increment in the velocity. So this will be the best ideal for a Runge Kutta. So inside the ODE4 file, we actually write this kind of function inside the ODE4 file. So you can see we need to use a for loop to iterate point by point to get all of the solution. So this will be the first point. Then we get the second point. Then we use the second point as become our previous point to estimate if my current for the first iteration I should be equal to 2. So I use the I equal to 1 to get the second point. Then as I want to calculate the current point become the I equal to 3. So I use I equal to 2 to estimate what is the I equal to 3 point. So 1 point by 1 point after several iteration, then we can get all of the numerical method. So this will be the best idea. It is not very difficult, but you try to understand. So after this will be the best function for the ODE4 file. ODE4 file inside it actually implement this function, only this line, only this following line. But remember, in this we did not finish our code yet. We need to write a code, return the slope. So it will be the f numerical. This function should return the slope. So in the next slide I will talk about how to write the f numerical. So you can see I try to write the f numerical here in this block. F numerical should be it will be the velocity. It will be the differentiator of velocity. Output will be the differentiator of velocity, and the input will be the time and the current velocity. So the input will be a time and current velocity. So I will use m. equal to 1, v equal to 2, f equal to 3. So dv should be equal to our equation. Our equation will be the, you can see because m is 1 here, so I just replace this equation is something wrong. You should write something like negative v multiply v over m and plus m f over m. So you should write something like this one. Maybe I can modify, direct modify, but it's a code. Remember this code is a little something wrong here. The equation here should be negative b over m because our equation is this one, f over m. Okay, you should write something like this one, not this one. But we get to the same result because m equal to 1. Okay, remember this part. But it will be fine because our equation is not this one. Remember, you need to be careful this part. So I can get a derivative of the velocity by this function, and I return the derivative, the differentiate of the differential of the velocity. So this function actually return the differentiated value. And then we can see the other part. This I create because I want to compare the numerical method. We want to compare the numerical method and also the analytical method. Analytical solution. So we also need to calculate the analytical solution. So I run a code to calculate the analytical solution. The time I create also from the 0 to the 10 second, and the time interval is 0.01, and initial value is y 0.1. So I also iterate from the second point to the end point, and I will directly use the function. This function is directly calculate what is the analytical solution of the velocity. So you will have a function called f exact. F exact will be here. You can see I put time inside. The function only time. This will be the analytical solution. Remember, we have this analytical solution, and the input will be only time here. So we put time here and MBF. Then we can get the exact velocity. So we get the curve, the array for the analytical solution. And then I try to plot a figure. First one, I plot the numerical method. Second one, I hold down and I plot the second. I plot the analytical solution, and the legend will be first line will be the Runge Kutta fourth order method. Second line will be the exact result. Then X label is time, Y label is velocity. Okay, so this will be the demonstration for the Runge Kutta method in the MATLAB. This will be the whole code. You just need to modify this part and also this part. Other part you can keep the same. It will be not very difficult. So I already give a lot of hint. You just need to modify. Other part, maybe the initial value you will also need to change. In the previous slide, the initial value you may need to change. And also the derivative part, the function for the slope should change. The analytical solution should change. Okay, so I feel it's not very difficult now. You should try to do that by yourself. So your solution should look like this one. We will have Runge Kutta and also the analytical solution calculated by the Laplace transform. You should look like this one, and your x-axis should be t, and the y-axis should be v. You can also draw like this one, normalized by tc, the shutdown time, and normalized by the L over tc. Okay. So it should look like this one, and you can compare this one. Maybe this one the time interval is 0. It will be, you can see the time interval will be 1, 2, 3, 4, 5, 6, 7, 8, 9. It might be 10 point, or not. Let me check. It's from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for this solution, it should be the time interval should be the 0. It will be 1 second. We have 20 points, so it will be the 0.05. And you can try to change the time interval, become 0.1, become 1, and let's see what will be the solution. Okay. And remember, we have the problem J. We need to calculate the work and the energy. So when we have the velocity function, if we have the velocity function and multiply the force, we also have the force function. Multiply together will become power. We already have the power function. We don't need to do the multiply. I already give the power function. If I have the power function, I integrate from the 0 to certain time. I can directly get the total work done during this time interval. So first one, we will get this one. So we need to implement the integral inside the MATLAB to help us calculate this function. And we also need to calculate and remember we shut down the engine, so the work done by the motor is become it will become 0 during as the time larger than TC, the shutdown time, after the shutdown time. So this power becomes 0, so we only use the power function to integrate from 0 to Tc to get what will be the work done. So the work done by the motor should look like, the solution should look like this one, because after the Tc we shut down the motor, so it will become constant value. Okay, the total work done during the time duration. And the dissipated energy, you will use this equation. So it will be the damper coefficient and the velocity power 2. We have the velocity function, but we have two velocity functions. Will be the before shutdown and after shutdown. So you need to also summation two integral function. The kinetic energy will be 1/2 mv power 2. Only this function. You don't need to do the integral. You just need to directly multiply the velocity, do the power 2 for the velocity. Then we can get the solution. But we all still have two power. 0 to, it will be the 0 to T0, 0 to TC to the certain time, the end time, the stop time. Okay, so you should use two functions to, the first one will be, the first part should be increase then decrease for the kinetic energy, and the total energy should be the input energy feed into the system energy and the dissipated energy from the systems, and also the transfer to the kinetic energy. So it tells us the total energy feed into the system should equal to the dissipated energy, also plus Wt should equal to the dissipated energy, also the energy transferred to the kinetic energy. So the summation for the whole, so if you use Wt minus dt minus kt, you will get the energy balance should become 0. The energy is balanced. So the solution should look like this one. The work W, the minus dt, and you can use draw the minus dt or draw the dt. It will be fine, but you need to you may you may draw this line like this one, but it should be dt, not minus dt. Okay, you need to be careful. So your legend, you should put correct legend here, and the kinetic energy will be this one, and the et should be wt minus dt minus kt. It should become 0. So your solution should look like this one, and the x-axis and y-axis, it will be not like this one. This one is already this part one already normalized by Tc, so the time will be T over Tc. The energy will also normalize. You can give me the solution. It is not normalized. So after I talk about this, the solution should look like this one. So how do we do the integration for the dt and or wt? So after we talk about the solution for j, now we will talk about how do we write a function to do an integral. So I will teach you two methods here. One will be the numerical method. The other will be how do we get an analytical solution for the integral function. So you can use the first part or use the second part. It will be fine. And so you can see if I use first part, I give you an example. The example will be the 1 minus ex exponential minus t. And so after we have this kind of function, we want to, let me read. This function here, actually the function fun, actually it will be the handler. We call handler in the MATLAB. We call pointer in the C++. And it means the representation of the function. So following will be a function. This is the other way to write a function. So if I use this at symbol, it means it is a handler or pointer. And then the following part will be the input for the following function. So this will be the following function. It will be the 1 minus exponential minus t will be our function, our integral function. Okay, so if I have this function, I want to do the integral for this function 1 minus exponential minus t, and I want to integral from the t1 to t2. In the MATLAB, we will use a function called integral. So the first one will be what is our function. I will put this function here. It will be just this one fun. And the first one will be the integral duration from the first initial time to the end time. Okay, so this function actually return the, if I have 1 minus exponential will be look like this one. This is the original function of t, and after the integral function of t, it will return the for example, this one will be the, for our problem will be 0 to t I. It will return this area and put the values in here, t I. Okay, he will only return one value in as time equal to ti. So for example, for the first point will be I equal to 1, it will be 0. So it will return a value as the, so the first function here may be 1. And I equal to 2, it will return the time actually is 0.01. Here will be 0.01. It will return a second value here So it might be increased a little. It will be here, and then third, it will return the value integral from 0 to 0.01. So it will return the value, so you can get a second value, then return, then iterate until to the time, so you will get another point. Will be the integration value along the time. Okay, so you need to understand this function only return the certain. This function only return one value. It will be a certain n time or a certain duration time. So it will be a certain n time. So I need to do the iteration to calculate each point, each time point from the beginning until to the end time. The end time should be certain. For this example, will be the 1 second. For your homework, you need to define what will be your duration here, and then what will be your function, what will be our function, and then run this code here. So basically, you just need to modify these two functions. This part you don't need to do anything. Okay. But it will not just write this only function, because remember we have part 1 and we also have part 2, so you need to write two this function, and then the time will be 0 to tc and the tc to ts. So it will be, you will have two parts, not just this part. Okay, so for the second part will be how do we get the analytical solution for the integral function. So you can see I use the SYMS TC. SYMS, it means I create a variable. The variable TC, it is a symbolic variable. It will be just a symbol. It is not any exact value or array. So my original function, I define it as a P SYM equal to 1 minus exponential minus t. So then you can use the exact function after the symbolic function after the, if it is w, I call w the wt function, I call wt exact function should be equal to int, will be the integral we used to do the symbolic equation. So I use int. Int here will be an integral. It means it's an integral. I want to do an integral for a symbolic function. And after the integral, we will have certain constant here, c. Because we don't know what is the c, so we will need to use the initial value. Our initial value in this example, I assume it will be the 0. Okay, so as soon it is the 0, I will get the solution should look like this one. I will get the 0 should be equal to the c plus t plus exponential minus t. And so after I use this equation, we can get the c should be, when you put t equal to 0, we can get c, the constant value should be here. It should be -1. So we can try to get the solution from 0 initial time to the end time and use the exact solution we just get here. Okay, it will be the t plus exponential minus t plus c, and then we can draw all of the solutions. So this will be the second way to do the integral. You can use the first one or second one. I usually use the first one. Okay, it look like easier. So I hope the hint is good enough for you to solve the homework too. And